So, hi again, I'm Vandika, and today Blake and I would be doing the introduction into physics and maths concepts for the Essentials of Engineering workshop. I'm not sure if Blake could introduce himself right now, but I will be doing the physics concepts and then he would be doing the maths after. Anybody could just let me know if they're seeing.
Yeah, we're seeing.
Okay, great. So, I will be starting off with the physics concepts. Um, the objectives of my part of the meeting is to understand how physics relates to engineering, the introduction of forces, types of forces, Newton's laws, and the application of forces. So, how does physics relate to engineering? It's the physics aura, right, guys? Physics is awesome. Engineering is more physics or physics in use, so therefore it's more awesome. How is physics related to engineering? Engineers, in order to build and design and create, use physics concepts. So you need physics to tell us why the engineering things work. So engineering tell us how things work, and physics will tell us the why that works. So forces. What is a force? A force, denoted by the symbol F, is an influence in the form of a push, pull, or twist, which is exerted on a particular mass. The object or mass or body that is doing the exertion or that is actually um, exerting that influence in the form of the push, pull, or twist is called the agent of the force and is being exerted on a particular mass. And mass, in by definition, is the amount of particles or atoms or molecules in an object. I once saw this term that they said that mass is the amount of stuff in a thing. So it's just the amount of particles or atoms or molecules in a certain object. Since the force influence, which is like a push, pull, or twist, it could cause certain effects, that being change in motion, which could be the object could start moving due to a force, it could stop moving due to a force, or it could start moving faster or slow down, which is accelerate and deceleration, respectively. A force could change the shape or the size of an object. For example, a twist, like if you have a sponge and you twist the sponge, it's no longer going to be like that rectangular shape. Let's say that was the certain shape of a sponge. It would change its shape or size. So like if you push a spring together, it's going to change in length or change in size. A force could also bring about a change in direction. So example, a football moving along a track and you kick it the other direction, that kick, you're the agent of the force because you're kicking, you're providing that influence, and the ball is going to change the direction on the field. Um, and then finally, the turning effect, also known as moment or torque. The moment of force is defined, like by definition, is defined as the product of the force and the perpendicular distance from the line of action of the force to the pivot. So, for example, you'll see this in like a seesaw mechanism where you have the pivot in the middle and then masses to either side. And let's say two bodies of the same mass go on opposite sides. The formula for torque or moment is T is equal to F by D, force by the distance. So forces of the same quantity on either side. They want the force that is closer to the pivot, that's the smaller the distance. So hence the smaller the turning effect will be compared to if that force was on the further distance away from the pivot on the seesaw, the larger the moment. So hence the larger the turning effect of that force. Um, in physics, I know, I feel like in your mind, you might think that you know the difference between force and energy. And I think like everybody might know the difference between force and energy, but I feel like it's important to kind of get clear because this is where the physics police would come in and be like, what's the difference, bro? And then you have the condescending dog stare that, like do I really know the difference? So a force is like the push or the pull, like that influence that we were talking about before. And energy is the currency you need to make something happen. So you can imagine you're trying to move a couch, and the force is you actually pushing the couch, but the energy is what your body uses up to do that pushing. So, and when you actually move the couch, you did work. And work is done when a body is moved a certain displacement or distance in a specified direction by a force. So you move that couch over a certain distance using a force. So you did work in that case. Um, the force family, there are different types of forces, many different types of forces. You can classify them into two main sets: contact forces and non-contact forces. Contact forces: applied force, tensional force, frictional force, drag force, normal force. What is the applied force? This one is very simple. It's where you basically push or pull on something. So you actually apply a push or a pull on a body. For example, you open the door, and that's the applied force because you pull the door open. Tensional force is acts on like um a string or a spring when you pull it or push it inwards, and it acts also towards the point of suspension of a body. So a pull on a rope or a string or a wire, that's the tensional force as it pulls back along the length. So it's like tug of war physics. Um, Frictional force, I think this is the force that everybody knows, like the OG force. It's a type of resistance force, which means it shows up when two surfaces rub on each other and it opposes motion. Drag force is very similar to frictional force, and it is a resistance force and it does oppose motion. But drag force, we term it drag force when it is in a fluid system. So for example, in liquids or in air, when an airplane is flying in air, it will experience drag force trying to resist its motion. That's like air resistance. And then like the hull of a boat or a ship in the water, that's also drag force trying to um resist the motion of the ship forward. Normal force acts perpendicular on a surface. It's basically when two surfaces they rest on each other. For example, like a book on a desk, the book would push down with a certain weight, and the table will push back up with a certain weight. So the normal force is kind of related. I'm not sure if you all heard about the Newton's laws of motion, but the normal force kind of like acts with Newton's third law. If object A exerts a force on object B will exert an equal and opposite force on object A. And we would see that in a bit. I know I'm talking kind of fast, so sorry if it's too fast. Um, Non-contact forces are also called long-range forces because they act at a distance to each other and they usually generate a field. For example, you might have heard of the gravitational field, magnetic field, electric field. So the gravitational force, also known as weight, is the gravitational pull of the Earth that acts on all masses. So it keeps us from not floating away into space, and it also keeps the planets and the moons and the asteroids in that heliocentric or sun-centered elliptical orbits. The magnetic force is the attraction or repulsion felt between the poles of a magnet, and the electrostatic force is attraction repulsion also, but between oppositely charged or like charges. So electrostatic charges, positive or negative charges. The nuclear force, also called the nucleon interaction, is the force felt within the nucleus of an atom between protons and neutrons. And like as you go further into physics, you would discover that that force really helps with the like fusion and fission and what creates the sun and all the fanciness, that would go along with that. Um, okay, Newton's laws developed by Sir Isaac Newton, who was just a legend when it comes to physics. Um, Newton's first, so each picture on the slide is not the actual law itself, but it's just something to like remember the laws by. Um, Newton's first law, an object at rest will stay at rest, or an object in motion will continue in the same um, direction with the same uniform speed unless compelled by another force. So basically, why is it so easy to wake up? Um, why is it so easy to stay awake until 6 a.m., but so hard to wake up at 6 a.m.? Because when you're awake and you stay awake until 6 a.m., that is like inertia. So inertia, Newton's first law is also called the law of inertia. Inertia meaning that um like a body would just want to continue. It don't want it resisting to change what it was doing. So a body at rest would want to stay at rest because it would resist trying to move, or a body in motion would want to continue in motion because um it would try to resist stopping. So it would be easier to stay awake until 6 a.m. because that is what your body was doing before, and harder to wake at 6 a.m. because you would want to stay at rest. Um, Newton's second law, this image here, force is equal to mass by acceleration, F is equal to ma, and that basically says that a force causes a change in motion. Um, and this is where like the action happens. So if you push a toy car, it would move, and if you push harder, it would move faster. That's Newton's second law because it links the amount of force, the mass of the object, and how quickly it speeds up. So if you have more mass, it would be harder to move. If you apply more force, you would have more acceleration. Newton's third law, and I said it a little while ago, if object A exerts a force on object B exerts an equal and opposite force on object A. That's just a fancy way of saying for every action, there's an equal and opposite reaction. So it's like this rocket you see in here. The gases move downward in this direction. However, it would provide like an applied upward force on the rocket to counteract the weight of the rocket, which is acting downward. So it will help the rocket push upward into space. So now, last part of my piece of presentation, the applications of forces. So roller coasters. I know you're seeing here LOCOE. However, I choose to pronounce it as just the law of conservation of energy in roller coasters. So I know we spoke about energy very briefly, but you see here gravitational potential energy, or GPE, and kinetic energy. That's like the two main um physics textbooks. Like that's the first thing you would see, like when you're doing your notes, and the first thing physics teachers will teach you. Gravitational potential energy is the energy stored in a body when it is above ground, and then kinetic energy is the energy a body possesses due to its motion, right? So the gravitational potential energy stored at the top of the roller coaster ride. So I'm not sure if you have seen the very faint roller coasters to the back here. The top is like here, you'd have a lot of gravitational potential energy because the maximum height above ground. So at the top is converted to kinetic energy as it dips. So as you roll down, you would increase in speed and increase in kinetic energy. So when you first, and now we'll talk about forces, right? When you first get pulled up like that big hill in the roller coaster, that would be the motor doing the work. It is applying a force to raise you up. So the motor in the roller coaster is applying a force to cause that initial rise. And at the top now, you gain the gravitational potential energy. And as the ride starts to descend, gravity now takes over. So that gravitational pull would change the potential energy to kinetic energy, which is the energy of motion. And that is why the ride would speed up as you go down, because that acceleration due to gravity is like pulling the ride downward. And then the crazy thing is what is happening to the riders. So you would feel like you're being pushed and pulled in your seat, especially when the roller coaster meets a sudden loop, like a drop. The riders will feel the force, and that is due to Newton's first law. Because if you're going in like at a constant speed in a certain direction, and then you force to change your direction, that is like that external force, which would kind of cause you to, you know, feel like you're being thrown around in your seat. Um, frictional forces and air resistance also act in roller coasters because the wheels of the roller coasters or like the tracks would be touching the actual like tracks that the roller coaster is moving on, and to create friction and then air resistance as well because you're basically moving through air, so that's like drag force would cause deceleration of the ride. And lastly, race cars. And something that you might know is that I just love Formula One. So like every opportunity that I get to talk about race cars, I would talk about race cars. So that's why it's in the presentation today. So we're actually shifting gears now to Formula One, where with the real life physics would begin, right? So friction on the track is the driver's like their best friend. And you might think not because you think that friction reduces speed of the car, and yes, it does to some extent, but the cars move so fast that friction would cause the tires to like grip to the road to avoid them skidding during acceleration or sliding during braking. Um and then they also use something called the cars itself use something called the aerodynamic downforce. And this is because of the shape of the car. It kind of looks like I have a picture here, not the best picture, but today. Um, the Yeah, so the shape of the car is like an upside down wing, and that causes the car to be pushed downward onto the ground. Because it's like an upside down wing, it has like a very wide base, low height, which decreases the center of gravity and increases stability. And this also increases the normal force that I was talking about earlier, like that force that acts perpendicularly down to the ground. So it will also prevent them from like skidding off the road. Um, and then the engines, what causes the car to really accelerate so fast? So with Newton's second law, F is equal to ma, is the force of the engine. So because the cars are very small and they kind of short, a little bit more lightweight than usual, the force, the applied force of the engine causes, since F is equal to ma and the mass is kind of light, the mass of the car is kind of light, the large force created by the engine produces a very, very large acceleration, causes the car to like increase speed. And something that also acts on the Formula One car is the lift force. Also, and they do something, a method called LICO. And I saw this in the McLaren driver, Lando Norris. He was talking about, like, he was explaining it, and I was like, okay, I'm going to include this in the presentation. So, LICO, lift and coast, is a method used to reduce drag. So, what would be going on here is that drivers would lift their foot off the accelerator before braking, keeping, and instead of keeping like the throttle pin all the way down, they would raise their foot off the accelerator, and this causes them to reduce the engine force and allow the car to coast. So when the car coasts, is like it wouldn't be going as fast. It would allow them to save fuel, and then the intense heat that the cars would have you created due to like the increased friction moving like on a straight road. When the car coasts, it allows them to like reduces the heat and it also reduces drag. So less engine output is equal to like less air resistance and less energy wasted. And I know that was kind of fast, but thank you all. That will be the end of my presentation. Um, so Blake, you're
Yep.
ready?
Thank you for bearing with me, guys. So today we're going to go into the mathematics and engineering portion. This is just a brief introduction. Our goals are to understand how different common mathematical concepts are used in engineering, familiarize ourselves with common unit conversions that are used by most engineers, and understand proportionality when scaling designs. Next slide. Okay, can you go to the next slide? Okay, so in engineering, there are general fields of math that are used and understood by engineers of all different types. There's linear algebra, calculus, differential equations, statistics, and probability, and then my favorite, geometry. Essentially, all of these allow for different functions of engineering that from complex data analysis to change of variables or systems over time, which can be looked at by pressure, how pressure will affect certain substances, and then using math for risk assessment when designing riskier builds or large buildings. Okay, next slide. So, although there is a general field of math, there is not so simple math that is used in engineering. Essentially, what these three examples state are that in engineering, there is such a broad range of fields within engineering that you can go into quantum, you can go into material science, you can go into thermodynamics, and there's a whole bunch of different specific maths that you will have to learn in each of these fields. So looking at these examples, we'll look at Schrodinger's equation. Schrodinger's equation is a way to measure the change in a quantum system over time. It is represented by the location, yep, the Laplace operator of a wave function, which is by the simple pi plus 8 pi squared times m, or the mass of a particle, times the energy minus the potential energy, times again of that wave function divided by the Planck constant, which is a constant used in quantum physics and quantum mathematics, divided by 2. And then that will always equal 0, and it will show you that this system or this quantum system is going to be definable by a predictable wave. And essentially, what this allows engineers to do is with medical technology and technology using lasers and different particles, engineers are able to identify how those particles work and then tune the technology to make sure that functions. Now, going on to material science, is we have Young's modulus. Young's modulus is an extremely important mathematical theorem in building larger structures, because without Young's modulus, we would not be able to understand the strength of certain materials. And if we use the incorrect materials to build buildings, they would be more likely to fall, and that would reduce safety for all of us. So Young's modulus essentially states that a measure of a material's resistance to elastic deformity, or how much pressure it takes for it to be stretched, is equal to the stress superimposed on the material divided by the strain superimposed on the material. Now at the bottom we have a stress strain curve. This is generally used by all the engineers, and the formula is not typically used, but this curve can often be a representation of different materials. Now going into thermodynamics, we have Fourier's law of conduction, and this is important when building certain designs that are temperature specific, and it's essentially just to show the heat transfer between two materials and how much insulation a material provides. Okay, next slide, please. Okay, so now we'll go into conversions. Why are conversions important? Well, at the moment in our dynamic workforce, there are engineers from all around the world. And as you know, in many different countries, there are also many different systems of units. So by understanding conversions and having common conversions available, you're able to work with people from a diverse background. Additionally, moving larger units to smaller units for simplicity is often a fun thing that people can do with conversions. Let's say you have centimeters, and instead of writing 2.43 centimeters for something, you can condense it down to 1 inch. So here are some common unit conversions. Length 1 meter is equal to 3.3 feet. You can read the rest. Next slide. So dilations and proportions. What are they? Well, when building, people don't start off with a gigantic design. They start off on paper, sketching things out with certain angles and then developing the blueprints. But how is this design going to be preserved for the actual construction? This is where proportionality and geometric dilations come in. With proportionality, the side lengths are always in ratio, the angle measurements are always preserved, and two objects might have different volumes, but they will always have the same ratio of side lengths and volumes. So what this means is, although they're like we see with this triangle demonstration, although these triangles are different sizes, they all look exactly the same and are just an increased or a scaled version of each other. Now, geometric dilations is a mathematical tool we can use to actually preserve this proportionality when scaling up from blueprints to larger designs. Okay, so that is my math part. Thank you.
Okay, thank you, Blake. I know. So that was it for the presentation this morning. I know it was kind of like an information overload. I would send this presentation after, and then it would also be on the Youth Team Advisors YouTube page. It will be posted later today. But because we love you all so much, there is an assignment, right? And we would be meeting on, I have it here. Um, we would be meeting on this Thursday, the 3rd of July, same time, 8 a.m. PDT, or 10 a.m. CT or 11 a.m. AST, and to present the assignment. So that will be a way shorter meeting. Basically, what you have to do is prepare a 3 to 5 minute presentation explaining either and the application of one of the non-contact forces. For example, like how does the magnetic field, which is a non-contact force of the Earth, works, or an application of one of the not so simple math equations in real world engineering. Um, so that's basically it. Like a short, very short, 3 to 5 minute presentation, nothing too long or extensive. You don't have to make anything to present either. You could just like talk it out. Anything is fine. But we would meet Tuesday for that. I'm gonna stop sharing now. Uh, yes. Thank you all so much for coming to today's meeting. It was so great getting to like meet and interact with you all. I hope you all understand everything. I know because of the shortened time in the meeting, actually we have like 8 minutes. Anybody have any questions about anything? If you all have no questions now, you could like get questions about the presentation, any questions you have, and you could ask us on Thursday as well. Oh, I know, looking at the chat. um, yes, great. Thank you all so much. If you all have no questions, you all could go. Thank you all so much again.
Thank you everyone for coming.